So this is Bitophysics number 64, the fourth in our 5-part series on quantum mechanics. And we are now today finally going to set wave functions in motion, see what happens, the time evolution of wave functions. So far we've been talking about energy eigenfunctions, which are simply solutions as a function of x that are stationary typically, and that don't really show the real features, the fun features of quantum mechanics, like tunneling, which is what we want to get to, and we'll next week. Actually, we'll be right on the cusp of it. Next week's show will probably be pretty short because all we're going to do is show some tunneling, and you're going to already know at the end of this show, if you don't already, how that's going to look. So on the first page, there's links to all the bytes of physics. Some of the early ones don't have audio. Unfortunately, Clubhouse misplaced things. I worry a little bit. I need to download all those things. I haven't done that. And there's also a few Nibbles of physics, which is a very small collection at the moment. And then just a link to all of my public documents, which are just occasional papers that I write and videos that I make. And then just post there for anybody to see. Yeah.
By the way, the bytes of physics that have to do with quantum and the nibble of physics we did yesterday on kinematics. They are already on YouTube. So I'm going to post the YouTube of the scientific discourse in the chat now. And you guys, if you don't feel like looking at boring slides, not boring slides, I shouldn't say that. I should say they're great slides that John makes. They're great slides. It's just that more fun when it's in video.
Okay. Yeah. Thanks, Shamash. I'll have to go look at that myself. I didn't realize how busy you'd been. Okay. So slide 2, the first one of content, is just kind of a quick review from last time. The key takeaway from part 3 is kind of 2 parts: that free particle energy eigenfunctions. This is so if I can solve the so-called time-independent Schrödinger equation for energy eigenfunctions. These are wave functions representing particles that have a definite energy. And free particle energy eigenfunctions are particularly simple because it's a particle that is not subject to any forces. It has the same behavior throughout space. We restrict ourselves to one dimension, so we're pretending that the universe has one spatial dimension. Things move only along the x-axis, and we might spend some time talking about generalizations, maybe in a follow-up at some point. But all of the key features really are there in one dimension. So these free energy eigenfunctions have a definite wavelength. They're sine waves, as we've seen, but they're entirely unlocalized. They have a definite wavelength, a definite momentum, a definite energy, but they are entirely unlocalized. It means that these are wave functions that represent particles that we know exactly the momentum and the energy of. And as a consequence of that, as it turns out, have no idea where they are. The only way you can know the momentum of a particle exactly is to have no idea where in the universe it's localized. That's one of the results of the Heisenberg uncertainty principles. And then number 2, we can create wave functions that do represent localized particles. This is really what we did last time, so-called wave packets, by adding energy eigenfunctions over a range of wavelengths. And that's what we did. We saw that a particle represented by such a wave function now has uncertainties in both position and momentum. It has uncertainty in momentum now because we are constructing it from many different many different energy eigenfunctions, as they're called. And so the energy could be any of those. It has more likely energies and less likely energies, but we don't know what its energy is. And the same thing is true for position. The graph at the lower right there shows you the collection of wavelengths that we could use to make a wave packet. You see there's a kind of a largest amplitude wavelength in the middle, and then I combine other wavelengths, representing other energies, other momenta, to the side of it in kind of a Gaussian shape. And there's something I won't go into the details, but the Gaussian shape turns out, if you make a wave packet out of a Gaussian distribution of amplitudes of different energies, you get a wave packet with a Gaussian distribution of probabilities for position. So it's kind of the way you get the minimum uncertainty in both momentum and wavelength, and they trade off, as shown at the bottom there in the Heisenberg relationship. The uncertainty in the position, which is basically the width of the wave packet that's shown at the bottom, times the uncertainty in the momentum, which is the width of the Gaussian distribution of wavelengths shown at the top there. That product is always greater than or equal to Planck's constant divided by 4 pi if you define those uncertainties properly as standard deviations, as it turns out. And so you can see in the middle there what you get when you add all those waves with those amplitudes. And basically what's happening is they're interfering destructively, canceling out everywhere except in that limited region. I'm adding waves that have amplitudes from negative infinity to positive infinity along the x-axis. But the excuse me. But the amazing fact is that when I do that, all of those waves completely cancel everywhere except in that limited region right near zero in this particular case. So let me just stop there for a second. Sorry, that was a little bit of a long review of last time, but any comments, or if anybody wants to come on stage, raise your hand and we'll bring you up. Okay, hearing nothing, let's get into it then. So how do we figure out the time evolution of this wave function? Well, we use the Schrodinger equation. That's what the Schrodinger equation does. It tells us how any wave function you might want to begin with, and you can begin with pretty much anything you want. Draw a wave function with a pen on a piece of paper. That can be your initial wave function. And this tells you how that wave function will evolve in time. The equation is written there, just so you have it on the second line. And on the first line, I tell you what it means. And what it means is you take the square root of -1, the imaginary number I, times the reduced Planck's constant, which is Planck's constant divided by 2 pi. That's what h bar is. That's just a constant. For our purposes, we don't have to worry about it. It's just a number. And then I multiply that by the rate at which the wave function is changing right here, right now. So that's what the little funny squiggle over funny squiggle t means below. That's read partial with respect to time, which means I take the derivative, the rate at which psi is changing with time at a particular value of x. So this is the rate at which the wave function is changing with time right here, right now, is equal to, I forget, I left out a minus sign there, equal to minus h bar squared over 2m times, and then it's funny the way it's written there. There's a little weird squiggle over weird squiggle with x squared and squared. That's read partial squared with respect to x squared. And what that means is when I let that thing operate on the wave function, which is outside, that gives me the curvature. We've talked about that before. Second derivative with respect to x is what that is. But now I'm doing it at a particular time. That's why the funny squiggles. So I'm going to take the rate at which the wave function curves right here, right now. So I take minus h bar squared over 2m times the rate at which it's curving right here, right now. And then I add to that the potential energy right here, right now, times the wave function itself right here, right now. Now, that's what that all says. And it's sometimes abbreviated, as I said below, as IH bar partial t of psi equals that funny little h with the caret over the top times psi, that's called the Hamiltonian operator. And that thing in braces is the Hamiltonian operator. And if you want some big words to impress your friends, you can say that, like all operators in quantum mechanics, the Hamiltonian is a Hermitian operator, the eigenfunctions of which are an infinite orthogonal set that is complete, meaning that you can use those eigenfunctions to construct any function you want. Okay, I just said a bunch of big words. We're going to move on. I have no interest in explaining them, but that turns out to be really important in quantum mechanics. Just trust me on that. Okay, that's as deep mathematically almost as we're going to get here. So I'll just tell you that the time evolution, we're going to talk here about the time evolution of free particle energy eigenfunctions. We saw last time that they're just sine waves. I wrote it out a little bit differently last time, but basically this is the same thing. Free particle energy eigenfunctions are sine waves of that constant, square root of 2m times the difference between the energy and the potential, which is constant if it's a free energy, if it's a free particle, divided by h bar, times the position. So it's a sine function of position, and that thing in front just kind of tells you how fast it wiggles with position. If I put that into the Schrodinger equation, it turns out to be pretty easy to show that the solutions are just, now that the wave function as a function of position and time is a sine function of that same thing. But you add in the so-called argument of the sine function e over h bar times t. That's really all you have to do, is just add or subtract e over h bar times t. And you can choose either the plus or the minus sign. If you choose the plus sign, what that actually is giving you is just sine waves that travel toward negative x. They travel to the left if you want, if positive x is in the rightward direction. And choosing the minus sign gives you a sine wave that travels in the positive x direction. That may seem like, why did they make it that way? It's not they didn't make it that way. That's just mathematically what it turns out if you do that. And the only content of this really is just to understand that free particle wave functions are sine waves traveling either to the left or the right, and you can read off of that. If you know how to, that the wavelength of these waves is as I wrote there. I should have mentioned that the momentum is just that square root of 2m e minus v is just the momentum, because E minus V, the total energy minus the potential energy, just leaves the kinetic energy if you have a free particle. And the kinetic energy in classical physics is 1/2 mv squared. So if I multiply 2m times 1/2 mv squared, I get mv squared. M squared, v squared, sorry. And then if I take the square root of that, I get m times v, and m times v, mass times velocity, is what we call momentum. So I'm just writing that a little differently. And you notice that in the second form there, it's really nice because you see that what I'm really saying is just sine of the momentum times x over h bar plus or minus the energy times time over h bar. And it is exactly for that reason, that combination of those things, that there is a Heisenberg uncertainty principle for momentum and position. The uncertainty in momentum times the uncertainty in position is always greater than or equal to some minimum amount related to h bar. And same thing for energy and time. You make a measurement of something at some time, the uncertainty in the time you measure, in the time that you measure it, and the uncertainty in the energy that you get as a result of your measurement, that product is also constrained by a similar Heisenberg uncertainty principle. So I'm just telling you a bunch of stuff to make contact with other things. It has nothing to do with what we're going to do the rest of the day. We're just going to now look at, we're going to have a movie fest. This is one of the days in school where the teacher hauls out out the when I was a kid, hauls out the film projector and then gets a film from the from the storeroom in the elementary school and shows films all day, and the kids just went, "Oh yeah, it's movie day." That's what I remember anyway. I guess these days you just turn on the video, and it's just everything's not as good as it used to be. The world's going to hell. Anyway, so let's then talk about what happens here. We talked about building wave packets last time, and with this understanding about the way the energy eigenfunctions from which those wave packets are built, knowing about how they move, I can now predict something about a wave packet. If I start with a very localized wave packet, I'm sorry, I'm not saying the slides. I'm on slide 5 now, Shamash. On slide 5 at the top, you see a very localized wave packet. And by the way, I should be calling your attention all the time to the fact that a wave packet kind of has an envelope. There's kind of a Gaussian envelope, both on top and on bottom if you want. And then within that envelope, the wave function itself kind of waves. So I'm creating a very localized wave function that has about 1 cycle or 1.5 cycles of a sine wave enclosed within a very narrow Gaussian envelope. And now and by the way, you know that this wave packet is moving to the right, because last time we learned that the imaginary part, which is the blue line, always leads the real part of the wave function. I didn't talk about imaginary and real parts on slide 4. But they both have the same character, sine waves, but they're separated typically by some phase difference. So this wave packet is moving to the right, and you notice that after a short time, the envelope has indeed moved to the right. The peak of the envelope is now 2 or 3 grid lines to the right from where it started out. And then there's another shot, another 2 or 3 grid lines to the right. And then a final shot, maybe another 4 or 5 grid lines to the right. But as it moves to the right, it also spreads. The envelope, the Gaussian envelope, and believe it or not, it still is Gaussian, is getting wider. It doesn't look Gaussian, but that's kind of an artifact of the fact that the high frequency or short wavelength, I should say, waves are traveling out faster than the low frequency waves. So you'll notice that as time goes on, the front of the wave packet is short wavelength waves, and the back of the wave packet is long wavelength waves. That reflects the fact that we don't know exactly what its momentum is. It has different momenta, and the low momenta, the long wavelength components are traveling slower than the high frequency or short wavelength components. So you see it spreading and dispersing so that the high frequency parts are in front and the low frequency parts are in back. I'll just ask you to kind of notice that, appreciate why you might expect that, especially the spreading. The spreading, just the result of the fact that since they're moving at different speeds, they can't stay in the phase relationship they had at the beginning, which was really special, designed to give me a wave function that had appreciable amplitude only over a limited range. So let me stop there at the end of slide 5 for a second. See if there's any comments.
Related to your last comment there about the waves traveling at different speeds, I'm trying to see it on the graph how it happens, and I'm kind of stuck because I always see the blue peaks like 2 millimeters ahead of the red ones, and this continues all over the place. So they appear to stay in the same phase relation.
That's right. We'll see some. I don't want to say that we'll see counterexamples of that, but it is an important thing to keep in mind, and then try to understand how it relates when it changes, when it's not that way. But in this case, where all of these waves are traveling to the right, it shouldn't be surprising to find the blue one leading the red one by a quarter of a cycle, roughly. So I don't know. Was there more? Did I miss? Was there a question, or was that just kind of pointing that out?
No, I just wanted to see whether we can see really on the graph how is it that the waves with higher frequency travel faster.
Right.
Because that's interesting. Usually people think of waves as they're all the same speed.
Right. Yeah, that's right. So light waves wouldn't do that, right? These quantum waves describing a particle. This is a particle with mass. There's a lot of things we could say about stuff that's called dispersion relationships, and we will talk. And this is a good time to introduce it. Maybe I should say it right now. In all the examples, we're going to be looking at videos from this slide on. Pay attention to the motion of the wave packet itself, the peak in the envelope, and the motion of the individual waves in that envelope. And you'll see when I set this in motion in a moment, you'll see how that happens. The speed of the wave packet is closely related to what's called, or the speed of the envelope, I should say, is closely related to what we call the group velocity of the wave. And it's the group velocity of a wave in relativity that can't be larger than the speed of light, because it's the group velocity that carries information that you can use to encode a wave, like in frequency modulation or amplitude modulation. The modulation moves at the group velocity. There's a wave that has its amplitude or frequency modulated in time. And it's not the wave that you listen to when you listen to the radio. It's the modulation which is taken off of the wave. And that's the thing that can't have a velocity greater than the speed of light. The actual waves themselves, the so-called phase of the wave, if I look at that red peak in number 1, in the first slide there, that red peak can move along at any speed it wants, as long as the envelope doesn't move faster than the speed of light in relativity. And I should emphasize, we're not doing relativistic quantum mechanics here, so you shouldn't necessarily expect our results to obey that. But that's something to keep in mind too. Let's move on and actually watch a video in number 6. Let me tell you what I've got going on here. What I have are 6 slides, 3 of which represent a low energy particle. Those are the 3 on the left. The 3 on the right represent a higher energy particle. I shouldn't say high energy, but lower and higher energies. And then as you go from top to bottom on each side, you can see I'm getting less and less localized. The top left is a low energy, highly localized particle. And then it gets less and less localized going to the bottom. On the right, at the top, I have a high energy, highly localized particle getting less and less localized as I go down. I had to go to some lengths to make this from the software that's linked to at the bottom there. We'll be doing a lot of stuff with that software today, and I really strongly recommend, if you want, as you see some of these videos, you might be inspired to go and play with it, because it gives you all sorts of control over a number of parameters and is really fun to get a kind of a sense of how this stuff works. So let's go ahead and just play this. All 6 of these waves are going to start moving at once. So if you play the video, you'll see the packets spreading out, all 6 of them spread out. All 6 of them have the high energy components running out in front. You'll notice that the high energy particle moves all the way off the screen earlier than the low energy one does. That is to say, the envelope itself is moving at higher velocity, reflecting the fact that it's a higher energy particle. So it has to be moving at a higher velocity. Excuse me for a second. Too much coffee this morning. Frogs in my throat. Okay, let's play that again if you like. It's probably a good idea to play it again and maybe stop it at some point if you can. Because I want to also call your attention to one other thing that's, well, actually, maybe I won't call your attention. I'll just ask you to, let's just take a minute, let you guys run it if you want. If any questions occur to anybody on stage or anybody in the audience who wants to put them in the chat or come up on stage and share them. There's at least one really interesting thing to notice here. And I'll just see if anybody notices it. Or something else, because it's not only one thing, but there certainly is one thing.
Hey, apologies, I'm jumping back and forth between screens. What link in the slides gets you to the video?
Say again.
What?
Oh, if you just click, so I've actually embedded the video. Hopefully this is working for everybody. I've embedded the video in the document. So if you just click on the video itself, it should start playing. Tell me if that's not true. Okay, at least one LT says that that's working for him. Is that working for you, Andy? I know you're probably off. Yeah, that's the problem. Sometimes when you're on your phone, you have to switch back and forth.
Yeah, I'm going back and forth here. So I might be on the wrong thing. What slide are we on here?
So we're on slide 6. It's the first one with a video. Okay. Let me know. Does somebody using a phone? Is anybody else? Raise your hand if you're having trouble making the video work. Because it's the first time I've tried this, and I think it should work in general. I think there. Yeah, what I do think here, one other thing I'll just mention is if you are on your phone, it's probably better to open the slides outside of Clubhouse. Copy the link to the slides from within Clubhouse if you need to, and then open a browser window outside Clubhouse so that you can just switch back and forth between your browser and Clubhouse. That might make things a little easier.
I got it now. It wasn't clear to me. I'm actually doing it on my phone in the Google Workspace app that I didn't even know I had, but I guess I did.
Oh, yeah, I don't think I know about that either. So let me just call your attention to the thing, to the one thing. Well, actually, I won't call your attention to the thing I had in mind. First, I'll ask you just to notice. And you can look at any of them, but you might as well look at the upper left, the low energy, highly localized thing, and tell me which is faster, the envelope or the individual waves. Which one is moving faster? And you can do that by looking, say, at that prominent red peak and just see how that red peak moves. You notice that the red peak will end up at the back of the wave packet in very short order and then kind of squash out to nothing. And new red peaks come up in front of that. It's a little hard to see the envelope, but the envelope is moving out away to the right very quickly, outstripping the red and the blue peaks very much. The so-called group velocity of that wave is much faster than the so-called phase velocity. The velocity that the individual peaks move at is much slower than the speed at which the envelope of those peaks move. Hopefully you can kind of see that. There's one other thing, though, and that is, this is the thing that I really did want you to look at. Notice that if you look once again at either one, but it might be simpler this time looking at the right. If you look at the envelopes, originally, of course, there's a very highly localized one. less localized, and then very poorly localized at the bottom. But as time goes on, very quickly, the highly localized one becomes less localized even than the poorly localized one. It spreads much quicker and is very quickly the most unlocalized wave packet. So it starts out the most highly localized. It ends up very quickly being the least highly localized. And you should be able to kind of understand why that's the case. The reason it was highly localized was because it had a wide range of energies. It takes a wide range of energy eigenfunctions to create a highly localized wave. And since it's such a wide range, some components are moving very slow, some components are moving very quickly. In fact, in kind of the worst case scenario, you could even have components that are moving to the left. So that thing could not only move to the right mostly, there could be parts of it that are actually moving to the left. So the envelope can spread so fast that it's spreading faster than it's moving, and therefore parts of it are actually moving to the left, reflecting the fact that it has components that are like that. Okay, let's see. Oh, yeah, so Michelle's doing what I did there in the chat, opening the document. Another browser actually does make things, I think, quite a bit simpler. Okay, any comments on that before we move on? It's just kind of seeing the interplays between envelopes, localization, energy. And you should see that, as I say, the high energy packets move faster. That is, the envelopes move faster. They have shorter wavelength waves. The primary wave is shorter wavelength. That's what it means to be high energy. And as time goes on, the more localized it starts out, the faster it spreads. So quickly becoming the least localized of the three. Okay, so let's move on to slide 7. In slide 7, I'm actually showing you now, these are zero energy wave packets. And you can tell that they're zero energy wave packets. You can tell that they're not moving. I wonder if anybody can tell, just looking at even before you run the video, can anybody tell me why you know that these wave packets aren't moving? They're not moving to the left, and they're not moving to the right. Because if they were...
The blue part would be following in somehow, and then there's nothing in the blue part?
Exactly. There's no blue part showing you for the red part to follow, right? It's a little... And you'll see when we actually put this in motion, the blue part doesn't stay zero, but it never leads or lags except on the periphery. So now I have a very highly localized zero energy wave packet and a very and a less localized zero energy wave packet. And if you run that video on slide 7, you'll see that very quickly, immediately, in fact, waves start traveling to the left and right symmetrically. And the waves that are traveling to the right have the blue, the imaginary part, leading. The waves that are traveling to the left have the blue, imaginary part, leading, right? And in the middle, there's just kind of a constant value. I should mention, as we'll see in subsequent slides, that the probability of finding the particle at any given place is the sum of the squares of the red and the blue parts, the imaginary and the real parts. If I just square them both and add them up, I get the probability of finding them. And so there's always going to be a substantial probability of finding this particle at zero. That's where it started out, and it had no energy. So we should actually expect to find, and in fact, in a mathematically precise definition of what we mean when we say expectation value, the expectation value of the measurement of position is always that it should be right at where it started out. But that's only because of the fact that it's just as likely to be 3 units to the right as it is to be 3 units to the left. We're very unlikely to find it at zero, but that's the expectation value in the sense that if I add up all of the possible values times their probabilities, I find out that that if I did the measurement over and over and over again of position, I would find this particle always being, or not always being, on average being at zero, just as often 1 unit to the right as 1 unit to the left, etc. And so once again, just notice the way it spreads out symmetrically, blue leading in both cases, high energy parts moving out faster than the low energy parts, etc. So all these things that you should start maybe developing a little bit of intuition, even if it's just me telling you stuff. You should see the same thing over and over again. And maybe say, okay, yeah, I guess I can see that. Short wavelengths, high energy, moving out in front, blue leading the red, imaginary that is leading the real, and so on. So, any questions on that before we move on to 8?
Yeah, I do, John. So I'm a little hesitant to ask questions because I don't feel like I'm being a very good student right now. But I'm trying to follow along. The two different, the red and the blue curves, I was imagining that they were like 2 examples of a infinite set of curves, or something like that. But are they interacting with each other? Like, is the red one following the blue one for some reason, or how are we supposed to think about these 2 curves and how they relate to each other?
So it's not, first of all, let me just point out, it's not you being a bad student. It's me being a bad teacher and not knowing, kind of being scared to even talk about the fact that the wave function is a complex function, right? It's a 2-valued function of position, which we represent in using complex numbers, which just turn out to be convenient for all sorts of really good reasons. But the Schrodinger equation, you notice, has an I in it. It has a square root of -1 in it. And when you do these time derivatives, et cetera, it turns out that turns real parts, that takes real parts and makes them imaginary, takes imaginary parts and makes them real. It mixes them all together in a way that I just don't have any way of talking about at the level that I like to talk about things here. So I've just been kind of vague about that, just to say that the full wave function, both the imaginary and the real parts do have these sinusoidal, they have very similar characteristics. And the only thing I really want to say about them is that when you look at traveling waves, you can say something about what direction they're moving by looking at the relationship between the blue and the red, if the blue is leading, etc. And that's just me telling you that. There's no good reason to understand that. But yes, in every one, and we're going to see this over and over today, I'm always going to show you both the real and imaginary parts. The red is going to be the real part. The blue is going to be the imaginary part. And you're going to see all these things going on. You shouldn't worry about it too much. And in subsequent videos, we're going to actually show that so-called probability density, which you get point by point by squaring the real part and squaring the imaginary part and adding them. That's how you really get the probability density of the particle being in a given position. We'll see that next time we do one of these movies. I'm going to take a little excursion on slide 8, but then we'll get back to it. So rest assured, it's more me being a bad teacher than you being a bad student.
Well, we can share that responsibility.
Okay, so let's go on to slide 8, which is just the only one I'm going to show from the website of my friend Dan Schroeder. He's a really good guy at Weber State University in Utah, and he's got a really nice collection of physics software, which I have a link to there at the top. And in particular, I'm looking at this one that's linked to at the bottom. And what I'm going to do, what this does is basically allows you to draw wave packets using your mouse, and then set them off. And these wave packets are going to live inside a big infinite square well, as we're going to see in subsequent slides. When a wave function hits an infinite wall, a wall beyond which the potential is infinite. We talked about this in the first one or two segments of this series. It reflects off. And so you'll see your wave functions reflecting off of either wall and just moving in the other direction. They literally, something weird happens while they're reflecting, related to what we call standing waves, because you now, during the reflection of a wave packet off of a wall, you have the back part of the wave packet still moving toward the wall, while the front part has already reflected and is moving the other direction. And when you have waves traveling in opposite directions, you get what are called standing waves. And I think you'll see what I mean here and in other, well, I know you'll see it by the end. But just go ahead and run this. This is just me playing with this software. You draw wave packets by clicking somewhere and then dragging your mouse. You click somewhere to create kind of the size, and then you drag it off one way or the other to give it a direction. And you'll see I just kind of randomly creating wave packets and then clearing it and starting new ones. You'll see all the characters that we've already seen in these wave packets, the way they spread, the way the high energy parts move out in front. But now you're seeing also these weird standing patterns that occur during the reflections. So you can play, if you go to this particular software, you can do this. You can just play around with this yourself, launch these wave packets and see how they interact. And just all sorts of fun little things that happen. You start to kind of get an intuition for wave packets. In particular, just do notice the standing waves that I'm talking about. Whenever a wave packet reflects or interacts with another wave traveling the other direction, you get these jittery kind of in place oscillations. They're for a moment, they're not traveling oscillations. They're kind of jittery in place oscillations. That's characteristic of two waves traveling in opposite directions, interfering with each other. And all this stuff, I should mention, I mean, as far as all that goes, this is just entirely 100% identical to what happens when you pluck a string. If you just look at one or the other of these, either the real or the imaginary part, the way it behaves is exactly what would happen if you just launched a wave like that on a taut string, like a guitar string, and you actually had the ability, to watch it. Even though it travels way too fast to be able to watch. This would be like a really slow motion version of a wave on a guitar string. It's exactly the same physics. It's exactly the same math. It's not exactly the same physics, but the math is identical. So let me stop there for a moment. Okay, I'll move on to 9. Now in 9, I'm going to go back to the same software I used before, but now I'm showing you the whole screen. This is the same software I used to generate those little pulses in the middle. But this is what the whole thing looks like, and it shows you all the kinds of things you can do. This is, in this case, I have picked, notice up at the top right, I've picked a step potential function. So I've picked that as my potential background. I've got little arrows there. I can bring the lower, I can bring both of the levels up or down. I can move the step position to the left or the right. And then there's a final arrow there on a green line, which represents the energy. In this particular case, I've chosen, if you look in the middle or down toward the bottom in the right there, it says electron wave function form. I can choose a wave packet, or I can choose a so-called plane wave. A plane wave is the name they're giving here to what I've been calling an energy eigenfunction, a pure energy sine wave. So that green line represents the energy that I'm choosing for the pure energy plane wave that I've chosen. I've chosen electron wave function form to be a plane wave. And the waves are coming in from the left toward the right. They're coming in toward that step, and that step is higher than the energy of the wave function. We talked in segment 1 about how if this were a classical system, the particle simply could not be anywhere to the right of that step because it doesn't have enough energy. Its energy is less than the potential of the step itself. That's a forbidden region. But I have a plane wave coming in, a sine wave coming in from the left toward the right, and it hits that step, and let's just see what happens. So you can play it, and you'll see that what you have here are pure standing waves. Oops, I'm sorry, and then I do something else. Just if you just play the beginning of that, maybe for the moment, stop it after 5 or 10 seconds if you want. You'll notice that what's happening there is the wave is coming in. It's entirely reflecting off of that barrier. And the reason it does is because that barrier goes on forever. The particle can't exist in that region. Notice that just like we saw in the first segment, the wave function actually does extend into the forbidden region a little bit, and it curves away from zero like we learned in the first segment. But because the barrier continues on and on, all it can do is head towards zero and eventually kind of get so close to zero that it might as well be zero. And it finally says, okay, I guess I'm not going to make it through this barrier. It gives up and comes back. And so the reflected wave is exactly the same amplitude as the incident wave, and that leads to these standing waves. You notice at any given time, you either have pure imaginary or pure real or some sum of the two that always add up. If I square the two and add them, I will always get that black line at the bottom. And that black line at the bottom represents the probability of finding this particle at any given position. And here what you see for the first time is a really weird quantum mechanical effect, and that is that when I shoot particles in at a barrier like this, I literally will never find them at some places. There are places there where the probability of finding them is always zero, and other places in between where the probability is maximum. This interference pattern between the counter-propagating waves that produces that standing wave is what gives me that result. So that's what you see in the first part, is just this wave coming in with this low energy, completely reflecting, giving me a standing wave. And now what I do after about the 7-second mark is raise the energy. And you'll see exactly the same thing happening until stop at 14 seconds or before. It's exactly the same thing, except now the standing wave pattern is shorter wavelength because it's higher energy in that region, higher kinetic energy, higher momentum. But once again, it completely reflects. The only difference is that it extends further into the forbidden region because it doesn't need much more energy to live in that region. It's only slightly forbidden from being in that region. So the wave function extends further into the forbidden region than it did before. So if you back that up to like the 7-second mark or before maybe and play it, you'll see me raising the energy, and then you'll see once again standing wave pattern, wave now extending further into the forbidden region. And then after about 15 seconds, I raise the energy. So now the energy of the particle is greater than the step potential. That means that the particle now can exist in that region, and therefore it does. And what you'll notice now is that you have a slightly different character on both sides. From the like 15-second mark on, when the energy is above the step, I have a purely rightward traveling wave, because the wave is coming in from the left, it's traveling right. If it gets past that step, it just keeps traveling to the right, and that's a purely rightward traveling wave. You can see that because it has no standing wave, no kind of standing in place kind of character. Meanwhile, the wave on the left side of that barrier is a little bit of a standing wave and a little bit of a traveling wave. If you look at it really closely, you'll see that it looks mostly like a standing wave, but on every oscillation, a red peak will kind of come down and then swoosh forward and then swoosh forward again. It kind of stays still for a moment, and then when it's at low amplitude, it swooshes forward, and then the blue one does the same thing. So if you look at that wave, you'll see that it's kind of traveling to the right, but mostly a standing wave. And that's because it's not now 100% reflected. There's a little bit of reflected and a lot of incidence. The incident wave is high amplitude. The reflected wave is now lower amplitude because some of the wave gets through. And that's what leads to the character that you see there. So there's a lot of things going on in that graph, but I mainly wanted you to see what happens when I change the energy from below to above the step. The fact that even when I'm above the energy of the step, I still get reflection. I got pure reflection until it was above, but now that it's above, I actually get some part of the wave function that just continues traveling to the right, because now that's an allowed region. Okay, stop there for a second, catch my breath, and entertain questions.
So after it crosses that barrier, its energy drops because we see that the frequency has decreased, but the amplitude is still the same.
Let's see. So let me see. So the amplitude exactly the same? Let me go. I can't remember. I guess that's, let's see, is that right? Oh, okay. Now see, right now I'm, yeah, right. This is a good, there's some things going on here that I don't immediately, I have to think about a little more. I didn't think about them enough coming in. You're asking good questions, Shamash. This is just the bad teacher showing up again. The guy who doesn't know his quantum mechanics as well as he should.
If you need help, I know at least one Clubhouse member who really knows their quantum mechanics.
Yeah, well, there ought to be somebody in the audience who knows it better than I do, I would think. Yeah, anyway, that's right. And it should seem weird. I know it did seem weird to me at first. This part, at least, I did think about a little bit, that the wave is traveling so fast, right? Once it gets, notice that when the energy goes above the barrier, there's very little kinetic energy there. It has only a little more energy than it needs to be in that region. But look at how fast that wave is traveling, right? Now, of course, that's the phase velocity. That's not an envelope moving, so we really can't say anything about how fast the particle is moving. That's just how fast the wave function representing the particle is moving. And because it has a constant amplitude in that region, it doesn't really count for much. In fact, the let's see. In fact, when I look at the probability density, what does happen there? Okay, oh yeah, that's right. So the probability density, you notice, is constant in that region. Yeah, so I didn't really answer your question. I'll just say that's a pretty good question. Let's move on to slide 10. In slide 10 now, what I'm doing is the same kind of thing, but I'm now going to reflect off of a step down rather than a step up. And you get reflections off step downs just as much as you do step ups. I should mention that this is entirely analogous to what happens when light moves from air into glass or from glass into air. When light moves from air into glass, it's moving from a medium in which its velocity is high into a medium in which its velocity is lower. And when it moves from glass into air, it's moving from a medium in which the velocity is low into a medium in which its velocity is high. And this is entirely analogous, and in fact is represented by exactly this kind of math, a step down or a step up. In something kind of analogous to potential, but it's not potential exactly. And you get when light reflects, when light encounters a glass surface, it reflects off that glass surface. When light in glass encounters an air surface, it reflects off that surface. You get reflection every time there's a change in the so-called index of refraction, whether it be on the upward direction or in the downward direction. So in this video, I'm going to, I think, take the energy and change it from a relatively high energy to a relatively low energy. And now you'll notice down at the bottom, there are some new ingredients. There's a thing called R and T in the lower panel, the so-called reflection coefficient and transmission coefficient. With the energy in its initial configuration, where it's relatively high above the initial potential, we're going to get mostly transmission. You're going to see that the wave is mostly transmitted. You'll notice that because there's not much standing character to the wave. The wave is mostly moving to the right everywhere, but there is obviously a little wave moving to the left. And you'll see that in the fact that there is a slight standing character to the wave on the left side there. So if you play the thing, you'll see that the wave is clearly moving to the right everywhere, but it's also kind of doing that little up and down dance thing that's characteristic of interference with a wave going the other direction. And then when I move the energy down to just above the barrier, now there's way more of a standing wave dance happening on the left side. It's also much longer wavelength because it's low kinetic energy, low momentum now at this point. That much larger dancing standing wave character is a result of the fact that there's a higher reflection coefficient. You'll notice that the reflection coefficient, after I lower the energy, goes up from the 0.03 that it was at the beginning to 0.29. That means 29% of the incident wave amplitude is reflected at that border, whereas 71% of it gets through. And I'll stop there for a second.
To be clear, it's being reflected on the border that it has already higher energy than that border. In classical physics, that should never happen, right?
Actually, that's not true. It happens in classical physics. Well, I shouldn't say, I really shouldn't say that. I think you're right. Yeah, I would say, no, I can't say.
If you have a ball and you're shooting it on top of a hill, it will never stop at the hill because you're already on top of the hill.
It's true that it doesn't happen for particles, but it does happen for waves.
It happens to light, I guess. Yeah.
It happens for light. Light, you could argue, isn't a classical thing, I suppose, but it also happens with waves on a string. If I take a thick rope and I attach it to a string, it probably won't surprise you that if I, hold that rope rope joined to a string, and then I launch waves down the string toward the rope, it probably won't surprise you that the waves on a string bounce off of the place where it's attached to the heavy rope. Even though some of it gets through, right? The heavy rope will oscillate a little bit because of those waves coming down the string. So there will be some of that. That probably won't surprise you, either one of those, but it might surprise you to know that if I do it the other way around, if I launch a wave, if I take the end of the heavy rope and I oscillate it up and down, launching waves down the heavy rope, it will create waves that continue to travel in the string. That won't surprise you. What may surprise you is that there is a little bit of reflection off of the string, and there's going to be some energy in that rope coming back at me just because there's been a change in the medium. And that's kind of, that's analogous to the index of refraction change going from air to glass or something like that. That's the same kind of thing. It's the same math. It's exactly the same math, even though the math may come from different places. One case it comes from mechanics. Another place it comes from electricity and magnetism or quantum mechanics. Okay, so I think that's slide 10. Let me see.
Just one more
one.
You technically cannot pull the green line below the barrier in this case.
That's right. Exactly right.
Yeah, okay.
I tried to do that, in fact, and it wouldn't let me. And that's because of my choice. Notice there in the middle frame on the right, I've chosen the direction of incoming waves to be from the left. You can't have incoming waves with an energy less than the potential in that region. Yep. Okay, so let's move on to slide 11. Now I want to introduce localization. I don't want to I don't want to have plane waves. I want to have a wave packet coming into this. And this is where this software, I think, really shines. You'll notice now that the green line on slide 11, the green line's a little thicker. This software actually kind of tells you how much of various energy eigenfunctions you're adding together to form your wave packet. In this case, I'm starting out at least with a not very localized wave, and a not very localized wave doesn't need a very large range of energies to create it. So the range of energies is, first of all, it's low energy, and the range of energies is all pretty close to that low energy. So all of the energies that I use to create this wave packet are well below the step height that wave is going to encounter. That wave packet is going to be moving to the right, and it's going to encounter this step, and all of the energy eigenfunctions that I've used to create it, not all, but infinitesimal amount, all but an infinitesimal number are smaller than the step height there. That green is actually a little fuzzy, as we'll see as we go on. So if you start this, you'll see this wave packet perfectly reflect. And you'll also notice the probability distribution down below. Look what happens to it. I'm sorry. Sorry, take it back. I forgot what I'm doing in this. In this slide, I'm not letting the wave packet move at all. We're going to do that in the next slide. All I'm really doing here is just showing you what happens to create that wave packet. So at the beginning, you'll see that I need a very tiny range of energies around that low energy. Then I'm going to raise the energy to close to the step height, and you'll see that at that point, let's just play this and see. So a very small range of energies near the low energy. Now I raise the energy, and to create the same wave packet now, I need a larger range of energies because it's a fraction of the center energy. And now I'm going to raise it even more. Oh, sorry, not going to raise it even more. I'm going to more localize the wave packet. So the first thing I do is raise the energy, and then I increase the localization. I decrease the width of the wave packet. When I decrease the width, the range of energies that I need grows even larger. And you'll notice that at the very end of this video, I have such a high energy to begin with, and I have so much localization that a lot of the energy that I need to create that wave packet is actually above the step in the potential itself. And those parts of that wave packet can exist in that region. So we'll see what happens when I actually set that in motion in the next slide. But I just wanted to really emphasize what's going on here. At the beginning, I have low energy, very wide wave packet, small range of energies near that low energy. Then I raise the energy still below the step. The range of energies increases proportionally, but stays below the step. And then when I try to localize the wave packet more, I now need to start using energies that are above the step. The green region grows, reflecting the fact. And you'll notice the green is very dense in the middle because I need a lot of that, and I need less and less of the wavelengths represented by the higher energies and the lower energies. But there's a very large band of green there representing the energies that I'm using to create that wave packet. Okay. So that's it. If you're all hungry to move on, we can.
Just very quickly, as you increase the localization, we notice in the wave function that the amount of waves that bounce and the amount of wave, well, they're not bouncing here, but as that green band, gets wider, I'm wondering whether if we let it move, more of those will get through now because I'm using larger energy.
You wonder no more, because that's what we'll do on the next slide. Okay, so in the next slide, I think what I do is I just start with a fairly wide, a not very localized wave packet coming in, and then I'm going to localize the wave packet. We'll see. So I start off with a wave packet that can be pretty well built from nothing but energy eigenfunctions lower than the step. You see, I just barely squeeze them in there. There are going to be some. That green just gets less and less dense as it goes up. But mostly I'm using energies less than the step. And so you should expect to see all of it, pretty much all of it, reflect off of that step. So if you put it in motion, I think you'll see that's what happens. You can see that it's a wave packet moving to the right. The blue is leading the red. You see the standing wave stuff going on as it interacts with the barrier, and then the wave packet reflects. And at the very end, you see the envelope, the probability function at the bottom, looks pretty much like it did at the beginning. Because number one, it wasn't, if you stop it now before it does the next part, if we just do the first part of that video, because it's not a very localized wave packet to begin with, it doesn't spread very fast. It actually manages to reflect off the barrier and then end up going the other direction without changing very much. It will have changed, but it won't have changed very much. It's spread. So except for the standing wave stuff, while the reflected front part of the wave packet is interacting with the not yet reflected back part of the wave packet, there's a little region of confusion there. And then at the end, it's just a wave packet moving the other way. The blue is now leading to the left at the end of that segment. And that's pretty much the whole story, because virtually everything that the wave packet was created from is from energies less than that of the step. But do notice that crazy standing wave thing while it's interacting. And then at about 20 seconds, I go in and I localize the wave. Notice what that does is it broadens the green. Now I've got a lot of components above the step. It's a much more tightly localized wave packet. Now it hits the barrier, standing wave stuff. And notice that what happens after the barrier is I have a wave packet traveling back, just like it did before, and a wave packet that continues to the right. And notice the interesting thing there is that even though those waves, let me check this out once again myself. Even though in some sense it looks like the waves traveling to the right, at the very end there, if you just look at after the localized wave interacts with the step, it looks like those waves are traveling really quickly to the right. But if you look at the wave packet itself, or you look at the probability density at the bottom, you'll notice that, number one, it's a relatively low probability. The stuff that gets through is relatively low, but it also doesn't move as fast. At the end of that segment there, at the end of the segment there, the peak of the wave function shoot, I screwed it up. Didn't mean to do that. Sorry, I lost my place. There. Yeah, the peak of the wave of the envelope on the right side actually doesn't move as fast away from the barrier as the peak of the envelope on the left side, the one that's moving back into the territory from which it came. So it can be very deceptive if you tend to look at what's called the phase velocity. The group velocity is a little harder to see because that's the velocity of the envelope of the waves, and especially when the envelope gets small, it's a little hard to see it. Okay, let me stop there, catch my breath again. But hopefully that all kind of makes sense. The localized wave has a lot of components that can exist in the beyond the step, and so they do. And then the rest of it reflects. So that was what was that? That was slide 12, right? Let's move on to slide 13. In slide 13, what I want to, 13 and 14, the last two things we're going to talk about today are trapping a wave packets in square wells. So I'm going to create a wave packet in a square well. Now, this is not an infinite square well, and one of the things we learned is that there are only certain energies allowed inside a square well. And you see now the green is now showing as discrete lines. There's only certain energies that I can choose. I'm going to create a wave packet that's mostly that darkest green line in the middle, but has little bits of the green lines above and below it. They get less and less bright as you move up and down. That's the top frame. That's kind of telling you what energies I'm choosing to make the wave packet that I've made in the middle frame. That's a wave packet traveling to the right. The blue is leading, as usual. It's going to reflect off of the right side of that well, and we expect it to because it has very little energy components that are high enough to exist beyond that step. And then presumably it's just going to kind of continue to go back and forth. Let's see what happens. And look at the probability density, which is once again that thing at the bottom is just the square of the red line plus the square of the blue line. It's the sum of the squares of the real and imaginary parts of the wave function. So we should see it moving to the right, and then we should see some standing wave stuff as it reflects off that wall, and then it should be moving to the left, and let's just see what happens. So there it goes, reflecting off the right wall, standing wave nonsense. Once everything reflects, we now have a spread wave packet moving to the left, bouncing off the next wall, spreading so much at this point that I can't even really recognize it as a wave packet. It's just at this point kind of waves reflecting. The high energy ones have gotten so far out in front now that they may be lapping the low energy ones at this point. And I just end up with kind of a crazy interference pattern between these waves that don't have, unlike in the infinite square well, where each wave has a frequency that's an integer multiple of the one below it. These frequencies are not, don't have that character. They're just a bunch of increasing frequencies, so they never actually match up again. That crazy, chaotic looking pattern will just continue forever at this point. Okay, so that's a fairly poorly localized wave packet in a square well, and the last slide, I want to first of all take the energy. I'm going to localize that wave packet more. That means I'm going to need to get more. That green region is going to extend up and down. It's going to extend so far up that I'm going to start adding in parts of the continuum. Any energy is available above the energy, above the well energy, above the higher potential of the well there. And so you'll see that. Just run this video. Notice that as I localize the wave, I'm going to grab the width of the wave packet and make it narrower. That extends the energies that I need up into the region above the well. And now when it goes to that side, you notice that a significant fraction of the wave function just continues traveling off to the right, blue leading. Then it comes and it reflects off of the left side. A significant amount still reflects off that way. And that's what's going to happen for quite a while. I didn't let that run long enough. But what you'll see is that if you let that go, wave function leaks out for a very, very long time, leaving pretty much just a wave function in the well that has lost all of those high frequency components. But once again, the kind of the steady state in the well is a very hard to predict combination of waves traveling in both directions. If you look at the wave that's left in the well, the blue is never in any obvious phase relationship to the red. They both seem to be just kind of oscillating almost randomly. So that's pretty much it for today, and we're only one step away from the goal, which is understanding the idea of tunneling and nuclear decay. But I'll just wrap it up with slide 15, where I'll just call your attention once again to the important features of the particle wave functions here. Number one, the trade-off between knowledge of position and the knowledge of the momentum and energy. When I localize a wave function, I need a larger range of energies to create that position, and vice versa. If I want to know the energy, then I have to sacrifice knowledge about the position, the energy of the momentum. I have to sacrifice knowledge about the position. Another important thing we saw today is this idea of group velocity, which is loosely the speed of the envelope of the wave packet, which represents the most likely region in which the particle will be found. So what I really want to watch, if I want to watch the motion of the particle itself, is that bottom frame, which is the probability density as a function of position. The most likely places to find it are the places where that function is highest. And then phase velocity, which loosely is the speed of a peak in either the real or the imaginary parts of the wave function. Sometimes phase velocity is so loosely defined that it's even hard to know what it is. But when you do have a traveling wave, you can kind of focus on a peak and see how fast that peak is moving, even as it may be getting bigger or smaller or something like that. And then finally, this idea of standing waves, those standing wave characters that are produced whenever you have counter traveling waves, especially those that are produced by steps in the potential, as we saw. And that's all I have for today. Thank God, huh? But lots of good videos, and once again, I can't emphasize enough. If any of this looks intriguing, it's really you can just fire up that software. It's very powerful software. Allows you to vary lots of things, and you can just play around with it, I think, and get some more intuition. If there's any aspect of this that you wanted to kind of wished you could play with, the good news is you can, because it's all right there in that software. I'm done. Comments, questions?
So, the one question that I feel I should ask, but I'm not sure if this will make sense. So the situation we have here is there's this well, right, which has some potential, and we accept that, the particle that we put inside this well, we don't know a lot about. We know some of its energy, within some certainty, and we know within some other certainty its position. And yeah.
No, I was just unmuting. I wasn't trying to say something.
You're just preparing. So the question is, all of these interferences that are happening, after you let the wave packet happen, is this the particle, interfering with itself? Like it's just stopping itself from being in certain places?
Yeah, I mean, that's effectively what you're saying. I mean, the point is that there is no particle, right? There's only the wave function, and the wave function tells us that if I make a measurement of this thing, which is going to, this is one, maybe I'm going to back up just a second and say, lots of people, of course, exclaim about the so-called wave-particle duality in quantum mechanics. And I think that's really misleading, because what happens in quantum mechanics is there are only waves. There are only the waves. But when I make a measurement that I mean to call, the position, I want to find out where the electron is. Well, I can do measurements, and those measurements basically consist of having the electron deposit its energy somewhere, have a collision with something, and make something happen. That corresponds to a measurement of its position, if you want. That measurement, where I'm going to measure its, quote, position as if it were a particle, is nothing more than it's represented by that probability distribution. I know that if I want to ask what's the probability that this electron collides with this thing or whatever, well, all I have to do is look at the wave function, which is what the electron is. And it'll tell me, well, if you make a measurement of this thing as if it were a particle, as if it was going to do something right here, well, here's the probability that you'll find that. So it's and I think it's even clearer in photons when you take a picture with a modern digital camera. A photon deposits its energy in a CCD, and one of the cells of your CCD array, and we say, oh, that's measuring, that's the photon, that's the particle. Well, all you're really saying is that there was in the quantum mechanical view of things, the photon is represented by an electromagnetic wave, or sort of say it and a bunch of other photons make up an electromagnetic wave. That electromagnetic wave has energy in it, and if that energy is ever to be deposited somewhere, that looks like a particle. When you deposit energy at one point, that's something particles do, but that's all that's happened. Is some energy has been deposited somewhere. So it's not that there is a photon. All there is are times when electromagnetic energy is deposited at a place. We call that a photon. And I think that's kind of that's the way to think about it. In quantum mechanics, it's not a wave-particle duality, it's a wave. And there are measurements of that wave that we interpret as giving us kind of particle-like characteristics, including momentum, right? Momentum and position are both things we associate with particles. But the thing itself is a wave. Okay, so other comments, questions? Hearing none, maybe we'll move toward closure. I see Benjamin has got a video there. Let me take a quick peek and see if it's relevant. Oh, no, I can't. It's got a. Oh, it does look like it. It does look like it's relevant. Benjamin, did you want to come up? Oh, is Benjamin here? He's not even here. Okay. Well, that's too bad. It does look like it's actually relevant to the conversation.
I watched that video yesterday.
Oh, so do you want to? Oh, there's Benjamin. So do you either? Maybe I should invite Benjamin first of all to tell me what it says.
No, I didn't get through it all. Let's hear from Andy.
Okay. What did you make of it, Andy?
Well, I think the guy is basically making a case, I think, for... let's see how to say this. I think there is a school of thought of like wave function realists who think that the wave function is the only thing that exists. And then what he is saying is like, actually, the wave function is a mathematical tool that doesn't actually exist, but is our way of describing what happens. So it's that, how much do you want to reify the math? And he would say that claiming that the wave function is the real thing is reifying the math too much. But I think it's also true to say that in the mathematics of quantum mechanics, the wave function is the thing. So I think it depends on which playground you're in, and or sandbox you're in, or however you want to say that. So it is an interesting talk. It's well worth listening to.
Well, I think that is really that's excellent, because it just allows me, I guess, to say what I probably should have said when I was saying all of that. I don't know how well I remembered to say this, but I always try to remember when I say something like there is no particle, there's just the wave function. I should always append to statements like that within the model we call quantum mechanics, because that's always what we do. The example that I usually talk about is people will say, well, are you saying, is space-time really curved? And I say, no, I'm not saying that space-time is really curved. What I'm saying is space-time is a real thing that is really curved in general relativity. Right, those are the things that need to be added. And so we have this toy model that we call general relativity that includes a thing called space-time, and space-time really is curved by masses and all of this. And then we take that toy model and we manipulate it to determine what would happen in it if we compressed solar mass down to 1 centimeter size or something like that. And then we look out in the real world and we see, well, are there such things? Do we see these kinds of effects in the real world? And then to the extent that we do, we say, oh, wow, cool model. Our model does a really good job of mimicking what happens in the real world. And it's very tempting these days when physics has got so many things so right. Quantum mechanics and general relativity are just stupendously successful models. It's really tempting to talk about them as if they are real, which is equivalent to saying that they are true, right? That this is nature. And so it's really important to remember that it isn't, or I shouldn't say it isn't, that we can never know if it is. And there really is literally no way to ever know whether it is. That's the important humility of science. Benjamin would disagree that science is humble, I guess, but
And he will do so with great confidence.
yeah, that's right. With humility, I'd just like to say science is not humble. But
Nice.
anyway, but I think I think that's an important point. So I'm going to enjoy watching the video. Go ahead, Benjamin.
I appreciated Andrew's review. I reviewed this video for any hint about the thing I'm interested in, which is the behavior of separated particles, entangled particles. And he really didn't get into it. He seemed to avoid it with great care. And I don't know how you could talk for an hour and a half about quantum and not talk about entanglement without meaning to. So he's not very interesting to me so far until I find out if he has a position on entanglement. Also, Looking Glass has started her course, her paid course, and I subscribe, so I'm looking forward to that.
Yeah, I don't know if you were here earlier when I said, so we're going to finish up the quantum series with part 5 next week. And I think it'll be relatively short after all the groundwork we laid, especially today. But after that, I think my plan is 2 weeks from today to devote it to kind of my enhanced understanding of the meaning of entanglement, questions of settled science and all that. And I invite you, Benjamin, to be there and to, I think maybe I might have a few things to say that you've never heard before. But because I've been sorting out my thoughts about all these things.
Where is this?
This will be 2 weeks from today here.
Oh.
Or at least that's my current plan. It'll happen for sure. I don't know for sure that it'll be 2 weeks from today, but it probably will.
My growing assumption is that your generation of scientists, and I've met several, are just kind of inadequate when it comes to data. They don't appreciate the data. They don't store the data. They don't understand the importance of the data. And as far as I can tell, they don't even know how to interact with the data. That's just an interesting commentary about a particular generation of physicists. I think the next generation of physicists will, in fact, be data-driven and more cognizant of the data. But that would be my assumption.
Well, I will. Physics has always been data driven, and that certainly hasn't changed. I know we disagree on those things, but one of the things I was going to say is that so I was going to talk. One of the things I want to talk about is the whole idea of spooky action at a distance, which I think there's a little preview of it. Spooky action at a distance is a name that we give to a phenomenon that has now been just completely 100%. Repeatedly experimentally verified. There is a phenomenon that happens. This has nothing to do with quantum mechanics. It's just something that happens. And that part, whether or not you talk about quantum mechanics, it's spooky action at a distance. It's the thing we call spooky action at a distance. That's just a phenomenally well verified experimental fact. And then the question is, how do we deal with that? What do we do with that? And number one, the question is it really spooky? Is it spooky when there's nothing spooky you can do with that fact? It's a weird thing. It bothers us for some reason that we can put our finger on. We can even put our finger on why it bothers us. But it's not clear why it should, because there's nothing spooky that you can do with spooky action at a distance. Since there's nothing spooky that you can do with it, it's kind of weird that it bothers us. And it's something that is completely irrespective of whether quantum mechanics is correct or not. The only feather in quantum mechanics' hat is the fact that quantum mechanics correctly predicts what you'll see. And what you see is this thing that we call spooky action at a distance. So I just think it's interesting to think about Well, anyway, I don't want to get too far into it. I need to still sort out my thoughts a little more. But I think it kind of starts with that whole thing. It's funny how biased we get by calling something spooky action at a distance that's not really spooky, I think.
Well, it is spooky because it violates the causal relationships that
It doesn't.
used.
See, that's exactly why it's not spooky. There is no violation of a causal, any of the causal things that we learn from
Well,
relativity.
typically things are close. If they interact, they have to be close. If they're at a long distance, it's very difficult to make them interact. You need like special parabolic mirrors, and you need all kinds of things to make distance work well. Things get harder at distance. But spooky
Yes.
action apparently just has no problem with distance. It doesn't even know the distance happens.
Well,
Or
see, you even talk about things interacting, right? It's not clear when you say things are interacting. I'm not sure what you mean by that. I think you have a mental model of what an interaction means. Spooky action at a distance is a name we give to an observed experimental fact. This is a directly observed experimental fact. And because then there's something about that fact that we find spooky. And as you say, and I mean, just as you say, it is easy to put your finger on what it is that you find spooky about it, even though there really is literally nothing spooky about it. There's nothing about the phenomenon that can be used to do anything spooky.
Well, it can't be used, that's true. But the fact that there is an interaction that can be detected is
It's that
sufficient
I just want to once again call your attention to the fact that you use the word interaction. There's no evidence that there's an interaction going on.
Well, if you think there's not an interaction, then you're Einsteinian. If you think there's an interaction, that the collapse of the wave function actually is a physical thing that causes states to change, then you're Borean. And I don't know if you've sorted out your own thoughts here, but I think you've got a foot on both sides, and that's fine. But
So I think
again,
I think
when
the
you
word
make the claims that this has been proved over and over again, I'll just point out, I'll make the claim that all of the raw data for all of that proof is not available to you or me.
Yeah, that's the conversation that we won't be spending much time on, because this is what always happens, of course, in science, is that people do an experiment. Somebody else says, wow, I don't think I believe that. Let me see your data. I mean, you can do that, and to some extent that's useful, but it's not nearly as useful as just doing the damn experiment yourself. And when the experiment is done hundreds of times and you get the same result from different groups all over the world, you call that settled science. Not settled science, a settled experimental result. Yeah, there are people
clearly got the opposite result.
Right. There are people that get opposite results who, for whatever reason, don't publish, usually because they don't have confidence in their results. Anyway, I don't want to belabor the point here. There'll be plenty more chance in a couple weeks. We can even get into the data a little bit, but mostly I want to just talk about the thing itself. By the way, one other thing I'll mention is that Tim Maudlin has a really good example. He says it's not analogous, and it's not. But it is this. It's the same kind of thing, right? You say, suppose you have 3 boxes into which you put either a red marble or a blue marble. You have red marbles and blue marbles, and you put red marbles and blue marbles. One of either one into 3 boxes. And then a friend picks 2 of those boxes and opens them, and there's a red marble and a blue marble, always, no matter which 2 boxes they choose. They never get to look at the 3rd box, but they open the 2 boxes, and they always get a red marble and a blue marble. And you say, that's weird. How could that possibly be? It's spooky. It's really weird. It's basically unbelievable. All right, you say, well, how could that possibly be? You put a red and a blue. You had to put at least 2 of one color, if not 3 of one color, in a box. How could it possibly be that every time into the boxes? How could it possibly be that every time you open 2 boxes, you get a red marble and a blue marble? That's really weird, and it is. It'd be really weird if that happened, but it has no import. There's nothing you can do with that fact. And that's kind of one of the things I want to concentrate on. Is one thing, I don't know whether that could happen or not. I'm tempted to say it couldn't happen. But on the other hand, that's kind of what you'd say about spooky action at a distance. And once again, suppose it could happen. It would have there'd be no consequences to that, at least none that I can think of. Maybe you can think of some. But I thought that was kind of a cool example.
That you would get with s equals greater than 2.
Well, I don't want to lose everybody right here, and I don't care if you get an S greater than 2. Frankly, all I care about is whether there's something you can do that's spooky with that kind of spooky fact, and I think there probably isn't. And to some extent, this relates to one thing we say about physics. I can't remember who it was that said this, but I think it's a really apt thing, and that is that anything that in physics, anything that isn't prohibited is mandatory. And what physics is not so much saying what can happen as saying what can't happen. And once you have gotten a list of all of the things that can't happen, everything else has to happen. It's just a question of, finding the right time and place for it to happen. But if it's not prohibited, then it's mandatory. And I think that's kind of gets at this spooky action at a distance thing. There's no reason to prohibit it because there would be no consequences. If you prohibited it, you would gain nothing. There's no reason to prohibit it, and therefore it's mandatory. I know that. I mean, that's a philosophical argument. We'll have to get Shamash in on this one. It's kind of like aesthetics, I think, but I rather like that idea. Anyway, more to come on entanglement. Oh, let's see. Dash wants to come up. Let's see. So I don't know how long your hand has been raised, Dash, but I'm inviting you. Oh, maybe he's there. There you are. Hey, Dash. Got something?
Hey, Professor, how are you? I actually just raised my hand. I just had I've been kind of in and out this lecture, this course, but I've been more so looking at the documents and stuff. So I have.
Oop, we lost you there. Dash, I don't know if you just stopped talking. I'm not hearing you. I think Dash.
Can you hear me?
There. I think you're back. Yeah, try again.
Okay, so you know how when we blast like photons through like the double slit experiment, basically.
Mm-hmm.
We get those 2 different patterns of behavior. We get the wave effect, but then we also get the particle effect between the slit, the medium that it.
John, forgive me for interrupting. Can you close your mic because there's a big.
Oh, okay.
Yeah, sorry.
Can you hear me?
Yep.
Yeah, it's
Thank you, and maybe it'll be better for everybody else now.
Got you. So I have a question. I was actually reading something about that, and I can't remember the physicist who spoke on it, but he was kind of giving his interpretation of why that happens. Like, why do we get both of those results? And something that he said was, it's because we're made of atoms as well. So based on particles, if you will, so that when we observe this phenomenon, this is why our particles, or this is what I was taking away from it, our particles, our atoms, and our energy, if you will, actually interferes or affects the end result of those photons hitting that screen. Would you say that that's an accurate interpretation or accurate way to look at things, or is it something less?
Yeah, it's not a thing I've ever heard anybody opine before, and it doesn't grab me very well. I will say this. So I mean, first of all, just the when you talk about the wave particle duality that's exhibited in something like the double slit experiment, it goes like this. You shine light at a double slit, and you form this interference pattern on the screen behind it, and you can explain that perfectly based on the idea that light is a wave, and it's done. You get everything. It works exactly right. But the weird thing is that when you dim the light, now you need some kind of a digital, CCD on the back or something to collect the light to see this. But what you find out, you just need some way to really see how the light creates pattern. And it turns out the light creates pattern by little impacts, right? If you have a film, if you literally photograph a film and you just did a brief exposure, you wouldn't be able to see it. You'd have to do it for a longer time, because the way the pattern actually builds up is by little hits. There'll be a little, if you have a CCD, you say, okay, I got a hit right here, something hit right here. We would say a photon hit right here. And as I was saying a little while ago, there's really been a deposition of energy, presumably from the electromagnetic wave that we call light. There's been a deposition of energy at this point. You say, okay, good, so there's a point. And then you wait for a while and you see other depositions of energy. And at first, it just looks like photons are randomly hitting the screen. There's no obvious reason for this point or that point to have been hit. And you might be tempted to just think, well, there's just light falling on this screen and it's just building up. But after you get enough dots, enough little hits, enough depositions of energy, you start to notice that there are lines, there are lines parallel to your double slits on the screen where dots are just much more likely to happen than others. And then there are lines parallel to those, kind of in between those, where there's just very low likelihood of any deposition of energy to happen. So the pattern, in fact, builds up through it's like a pointillist painting or something. You don't really realize that when you're looking at the screen in real time. When you shine a laser on double slits, there are literally trillions of photons hitting that screen every millisecond. And so you don't notice the fact. You look at it visually, you just see this pattern. But if you do it with very dim light, what you do, you see the pattern building up, and you notice that it is actually building up from individual impacts. I don't even want to call them impacts, individual depositions of energy. I don't know that anything's impacting. All I know is that there's been a deposition of energy at this point. We call those depositions of energy photon impacts, but that's just us naming something. The only evidence for which we have is that there's been a deposition of energy, and it presumably came from the electromagnetic wave. So that's why I say that the thing is the wave, and the wave tells us the probability of finding a deposition of energy at given places. And over time, those probabilities turn into certainties, so that we can, if I have trillions of impacts that are all obeying the same probability, then I will get something that has a very continuous looking, non-deposition oriented look to it. It just looks like this nice, smooth interference pattern. But I don't think I would say that it's because we're made of atoms or anything else. It's just because that's the nature of the way electromagnetic waves deposit energy. And it's also the way that you form electromagnetic waves are formed energy gets put into an electromagnetic wave from an atomic transition here. It gets put in from an atomic transition here. And pretty soon you have the spectrum of that atom in the form of what looks like continuous light, which has really been created by a very large number of little depositions of energy from atoms and electron wave functions into an electromagnetic wave, and then it comes out in a similar way. But I think the particle nature is just something we put on these depositions. It's Benjamin would say that this is very much a collapse of the wave function kind of a way of thinking about things. I don't think it has to be thought of in terms of collapse of the wave function so much, but that's certainly one way to interpret what's going on. Sorry, that was a long-winded answer. But the short answer is no. I don't think it has to do with us being made of atoms. It really just has to do with kind of the nature of how quantum mechanics predicts depositions.
Gotcha. Nah, thank you. I think that is clearing up a lot of fog for me. So basically, like, are you saying that with the naming thing, we give these discrete, we create these discrete units of packets that we call photons, but in reality, it's actually all waves, is what you're kind of saying?
Well, let me be clear. I'm certainly not saying that in reality it's all waves. What I'm saying is that in quantum mechanics, which is a model of reality, it's all waves. What it really is, as I was saying a little while ago, I don't think we can ever know. The fact that our model does such a good job of predicting things that we see makes it tempting to think that our model really is reality. And it doesn't hurt really too much to do that until it starts making you, until you get so wedded to the model that you think that you've got it all done. You've figured out what reality is. The moment you really do know what reality is, then you don't need to do any more work. Unfortunately, we'll never get there because I don't think we'll ever know what reality is. That's not our job. Our job is to be able to predict what will happen in reality using models that may have nothing to do. These are mathematical models. Does nature care about math? I don't know. It's weird that math works so well. Makes you think that nature does care about math, but it doesn't have to. All it needs to do is do what our mathematical models say it does. Or I shouldn't say that. All it needs to do is the same thing that happens within our models, and then we say, "Wow, it's a good model."
Got you. I actually heard a scientist by the name of, I think his name is Jim Gates or Sylvester Gates or something like that. He described mathematics as like almost like a sixth sense that humans have to basically interpret more layers of reality that we can't. To basically understand more layers of reality that we can't typically understand with our five senses. And that's kind of like my relationship with math. And in addition to that, I do have a question about the wave function. Or quantum mechanics, I'll say. Or two questions. So the first question is the wave function, right? Is this a way? Because I've been in a rabbit hole of just trying my best to understand, to the best of my ability, this branch of mathematics. Is the wave function? Is it a way of like transposing a list of data points? Like, could you simplify what it is, what exactly we're doing with the wave function through a mathematical lens?
Yeah, let's see. I don't know. I'm trying to think I may not completely understand the question, but I think it's more that it's what it is. It makes me want to actually tell you more of the history. I mean, how did people ever think that a wave function might be, quantum mechanics and its wave functions might be a good model of reality? And that's I just don't know the answer to that question. In the end, there's kind of it almost doesn't matter. To the extent that the model gives accurate results, it doesn't even matter what it is that the wave function is representing or means or anything else. We have this mechanism. It's the shut up and calculate mentality, if you want. We have this mechanism which we don't really understand the origins of, where it comes from, but it works. And so we use it. But it's certainly within the language of quantum mechanics, we simply say that electrons are quanta of the electron field, and photons are quanta of the electromagnetic field, and so on. Every particle is just every elementary particle is just a quanta, in the same sense that a photon is a quanta, the amount of energy that can deposited. It's a quanta. It carries the characteristics of a quanta of the field that it represents. And that field is the wave function for that thing that the Schrodinger equation says how it evolves. And somehow, for reasons I wish I maybe even understood historically a little better, it's weird that we got there. It's weird that people thought that that was a way to do it. But there's kind of no arguing with the success, or at least there's little arguing with the success. There always should be some arguing with the success, because there's so many things that we don't understand, like entanglement. What does it mean? You know, what does it mean? And does what it means point to a better theory? The fact that there are some things we don't understand does suggest that there might be a better theory that wouldn't leave us with so many questions, but maybe not. You know, maybe it's the best we can do. We don't know. So that was really not an answer to your question. Go ahead, Shamash. I knew this was getting into your territory with the bath stuff. So you go ahead and take it.
I'm just gonna try to keep it short. I don't wanna also delve a lot on it. But the question, what is the wave function and where it comes from? It's like asking what is a point in Euclidean geometry and where it comes from. And Euclid doesn't give a definition. And if you try to define a point, you say, well, yeah, it's a point. It's very difficult to say what a point is if you want to really be precise. So you want to say, oh, it's a zero-dimensional entity with no width, height, and okay, fine. How do we know what the dimension of a thing is? Right? Like you say, oh, but the definition of dimension is built on the idea that a point is zero dimension. Like dimension comes way later. It's a much more sophisticated idea than a point. And then you say, okay, how do I define a point? Does it mean that the lack of definition of a point, does it mean that Euclidean geometry doesn't work or doesn't or fails to represent real life situations sometimes? Or no, it doesn't. Just that those are essential starting points of the theory, and it's not very helpful to ask where they come from as much as to focus on whether they reflect reality accurately or not.
Understood. Yeah. Oh, go ahead, John. I'm sorry.
No, you go ahead, Dash. I was just going to say I thought that was good.
Yeah, I was just going to thank Shamash for that. It's almost like it's no pun intended, but it's pointless to ask these types of questions because it seems like
exactly
too philosophical. So I get it. I get you. I just have one more small question, staying here.
Okay, and then I see John has joined us on stage, so we'll go to him after that. Go ahead, Dash.
Okay, cool. Brockhet notation. So I'm just is Brockhet notation, because this is something that I saw on YouTube that I've been looking at. Is this the same as the wave function? Does this fall under quantum mechanics? What is that exactly? Well,
yeah.
What do you use that for?
Yeah, so the bra, and it's called bracket, right? The idea originally was bracket, and then it was divided into a bra and a ket, and fundamentally it just kind of refers to the wave function, and the bra is the wave function, and the ket is the complex conjugate of a wave function, or the complex conjugate of a wave function, I could say, and often what one does is well, I don't know how to even explain it. Maybe somebody else can better than I can. It's a way of looking at. Well, if for instance, if I want to No, I don't know. I don't want to say that either. I don't know what to say about it, frankly. It's certainly beyond the scope of the kinds of things that I want to talk about in here. I have to think about it. It's a good question, Dash. It's just beyond the scope here, I'm afraid. Anybody else have a good answer for that one? There should be I want an answer that people can appreciate.
Can you rephrase the question?
Well, do you know, Shamash, what the Brackett notation means? The idea is that oftentimes what you do is you operate on a wave function with a Hermitian operator, and then multiply that separates it out into its eigenfunctions, and then by multiplying the result essentially by the complex conjugate of the wave function, you get the expectation values. Oh, so many pieces of language. I don't know how to do.
Is the question about why phi star gives you the probability squared? Is this
Well, so that's a simple example. That would be a notation where you just have a bracket without an operator. Where the operator in that case is kind of an implied delta function for position, as it's called. But then, so if you just take the complex conjugate of the wave function times the wave function, that would be a bracket without really any need for an operator in between. It becomes useful when you start actually combining it with the operators for momentum or angular momentum or energy or position. Any observable quantity has a Hermitian operator that you can operate on the original wave function with. To kind of separate it out into the eigenvalues, into its eigenfunction representation, for then operating on with another wave function. I'm not helping. Anyway, let's move on. Let's move on from that. I think Dash was basically asking about a thing which is out there, the bracket notation, but I don't think it's useful for our purposes here. John, yeah, you go ahead.
Yeah, thank you. I saw you brought a very interesting point that reality is not as what we thought mathematics or any kind of formula. So in my mind, we observe something, observe the reality, and we try to use the mathematics to simulate this reality. And so based on if we think based on our observation, the accuracy of our observation of the reality, then we have the formulas to describe that. If we think the formulas can describe what we or can predict what we describe we observe the reality, then we thought, hey, this is a good theory. So as our accuracy increase, the reality of the reality increase, then we might find, hey, our observation, our formula might not work. So we need to find a better formula to describe the reality. So once we get to that point, that but my question is there any limitation? Our observation of the reality. We just cannot be any more accurate.
So a couple things. Number one, so I had two things I wanted to say about it. Number one is, I think, stripped to its essence, a humility in science requires us to really say things like this. We have these devices, for instance, called ammeters that tell us how much current is flowing in a wire when we hook a battery up to it, et cetera. Ultimately, we have these mental models of what that really means, that there are really electrons flowing in this wire. The ammeter is telling us something about how many is passing through it per second, et cetera. But ultimately, and just if we go back to an old-fashioned ammeter, which was literally a needle that pointed to a number on a dial, what our physical theories are intended to do is to say, okay, if I put this thing that we call a battery here and I attach this thing that we call a wire to its end and I run it through this thing that we call a resistor, and then I run another wire to this thing that we call an ammeter, et cetera. I want a theory that will allow me to put characteristics of that battery and that wire and that resistor and maybe even the ammeter, et cetera. And I want it to predict what number the needle will point to. That's if my theory can tell me that the needle should point to 3, then I say that's a good theory. Now, I don't care, I may want to say, well, that means 3 amperes. I don't care, right? I mean, ultimately, I don't care. All I really care is if my theory can tell me what number that needle will point at, then it's a good theory. All of my stories that I tell myself about the fact that I'm measuring electrical current and that batteries, raise electrons to a higher energy level, whatever, I can tell myself all those stories I want. I'm not measuring any of that stuff. All my theories want to do is tell me what numbers the needles will point at, irrespective of any interpretation we put. So there's that business, and I think that means that when we talk about reality, we're telling ourselves stories because we don't know. We have no idea what reality is, even though I think it's really useful to think we do. The second story I wanted to tell is one that I think about all the time. You talked about getting better theories. In some sense, if you look in the realm of gravitation and mechanics, we've only had 2 theories. The first was Newton's, and the second was Einstein's. There were all sorts of things. There were Kepler's laws, there was Copernicus, there was Ptolemy, all of these people just looking at patterns and just giving us empirical laws. But the first actual physics was Newton when he came up with the law of gravitation, which wasn't just intended to tell us how planets moved. It was intended to tell us, how stuff works, period, everywhere in the universe, how forces cause accelerations, how gravitational forces, where they arise. And it was really good. And it's so good that we will always use it because it's not only good, but it's simple. It's really simple. It gives us really accurate results. And whatever it means about reality, we don't care. We're going to use it until the end of time because there is no simpler theory that gives such good results as Newton. But we also know it's wrong. At the same time of all of that, we also know that it's fundamentally wrong because it makes a prediction about, for instance, the precession of Mercury's orbit that is minutely wrong. For a long time, it was thought, well, maybe it's not wrong. Maybe it's just that we don't know about some other planet that's tugging on Mercury that's making it precess more. Nope, turned out it wasn't that. It was that Newton's theory was wrong. It's wrong in a way that only starts to show up when you start having strong gravitational fields, and it shows up very minutely in the solar system when you're really close to the sun. And now we know it also shows up further from the sun because we have better ways of measuring it. And so we replaced Newton's theory with a theory that is fantastically more difficult to use, but makes all of the predictions that Newton's theory does and gets the precession of Mercury and just a bucket load of other things that Newton would get wrong right as well. And so the entire history of science really only has one correction. We finally came up with a scientific theory in 1700 and found out it was wrong in 1900, and we now have a new theory. And yeah, everybody always thinks, well, someday we'll find out that general relativity is wrong, and we'll replace it with something better. And that's probably the case. It might be the case, but I think it's really interesting to realize that it also might not be the case, because that story of replacing a wrong theory with a new one has only happened once. And I just think that's also it's worth kind of reflecting on the meaning of that.
Thank you.
Yeah, I don't know if I completely answered your question, but or your comment, but the things you said kind of brought those up in my mind.
Yeah, I'm just thinking about to see, is there any limitation for us to be close to the so-called reality?
Yeah, I think I think there's tremendous limitations when you start actually talking about anything where you actually talk about like what reality is. We cannot know. I believe, maybe I'm wrong, but science certainly works on the basis of understanding that we can't possibly know what reality is. All we can know is what it does.
So my question is actually is, if we reach the limitation, then we would not get have a better better theory, right? Because we already have this theory to explain what we already can measure or can see. So then we our science might just stop over there, because we can get more accuracy be more accurate to the reality.
Well, what happens, of course, is that so. What do most scientists do? Most scientists aren't actively looking for new theories, and aren't even really, in some sense. I mean, it's not. Most science is done by taking the theories we have and looking for, like in solid state physics, it's just really, really, really complicated quantum mechanics with, trillions of atoms and electron wave functions interacting and using statistical methods. And so you come up with little sub-theories. There's a million sub-theories that all ultimately respect quantum mechanics and general relativity, which are kind of the big duo. And they'll and I think there's no reason to think that ever ends. Applications of theory become theories themselves when they're complicated enough. So I don't think that ever ends. And then of course on top of it, there's no way there'd be no way of ever knowing that you've got it right. And so you would continue to look at predictions. There's millions of predictions of quantum mechanics and general relativity that we well, I shouldn't put it that way, but there are lots of things that come up that we simply can't test. We don't have any way of testing them. And until we do, we can't know for sure that they get them right. Lots of sub-theories in quantum mechanics. They're not really theories in quantum mechanics, but theories of particle physics. Hypothesize, more and more massive particles or something. String theories, right? That's the reason string theory is likely dead, or at least likely going into hibernation for a long time, because the only kinds of things it talks about are things that we have no way of testing. And until we do have a way of testing, it can't really be considered science. But, it's not that they're not still out there, and they do mean the fact that they're out there, the fact that there are things that we don't understand and always will be, means I don't think we ever come to the end of science in that sense. Anyway, we're waxing philosophical. We're impinging on Shamash's territory here. By the way, Shamash, do you want to talk for a moment about, I think I will start winding it down, but do you want to say a few words about your philosophy series?
Oh, please. Thank you. We have started since Wednesday a new club here, a new house on Clubhouse. It's called Philosophy Wednesdays. And it is exactly what it is. We will do John Mallinckrodt style rooms, scientific discourse style rooms, just like this one. We will have slides, we will have videos, but the topic will be more towards philosophy. So on Wednesday, we did an introduction. So what is philosophy? What does it study? And next Wednesday will be about logical fallacies and about how is it that we can arrive to those mechanisms, like why is it a mistake? And we will take more topics in the future. We'll talk about science, theory of knowledge, all that stuff, all the nice stuff that you probably are interested in. I can totally tell that some of you guys are interested in these topics. So these rooms happen every Wednesday at 17:30 GMT.
Same time as this room, I think.
Same
right?
time as this room, exactly. Yes. So you're more than welcome to join us. And this room and the other room as well will be on YouTube. You can follow the link. I'm going to paste it again in chat. The Scientific Discourse channel will have all of those playlists available for you to watch again. So thank you, and hope you all join.
And I should mention, I think Shamash didn't lean heavily enough on how different I think his philosophy, if you want, is from a lot of what I see on Clubhouse that usually just kind of leaves me running from the room screaming, because he really gets deep into things that always border on and are kind of grounded in, maybe, is that fair to say, Shamash, in math and logic. And I think that's, or at least the logic part. But I think, Shamash is definitely at the mathematical, logical end of the philosophical spectrum. And that certainly works for me a lot better than a lot of the stuff that passes for philosophy, I think, on Clubhouse. So, yeah, I encourage you. I thought it was really a good start.
If you watched the room last week, and if you haven't, you're more than welcome to watch the replay on YouTube. The whole theme was about to avoid this wishy-washy language that people sometimes use, and to differentiate between poetic language and philosophical language, because most of the time they're confused. And so you read a quote that sounds deep, and it's like, yeah, like, leave this life for those people to enjoy it, and you have to worry about the deeper things, the philosophical things, right? But it's not the case. Academic philosophy is about very serious problems. And whether you are an artist, or whether you are a psychologist, or whether you are a physicist, there's always an interesting problem on the edge of the methodology of those topics, and this is where philosophy lives.
All right. Thanks, Shamash. And thanks so much for everything you do around here. We're missing Ben today. I haven't seen much of Ben recently. I think
I tried messaging him since Friday, but he didn't reply yet. I think he's busy with family or something.
I think so too. Anyway, I'm hungering for a little more Ben in my life these days. But I think I am going to close it down. I was talking with somebody. Who was I? I think was it Andy? I don't know if was I talking to you about John Mayer? I was talking with somebody about John Mayer the other day. Well, I'm going to close with my most common closing. I don't call myself a huge John Mayer fan, but I am a guitarist. I'm a pretty good guitarist, but I'm not as good as John Mayer. And I think his guitar work on Gravity is just spectacularly nuanced. If you're a guitarist yourself and you understand anything about the difficulty of bending a note to just the right little fraction and giving it just the right little vibrato, John Mayer really has it nailed. So listen to the nuance, and we'll see you next week.